Hello everyone, welcome to my channel Student Success. This is Dr. Hussain. Last class I have discussed about the how single phase full wave midpoint configuration circuits will work for R as well as RL load. Now coming to that, why we are going for single phase full wave bridge type of configuration with R and RL load, I'll tell you step by step. First foremost thing is, if you people observe that midpoint configuration is required high voltage rating transformer, high voltage rating high voltage rating transformer. And second one, it 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 requires it requires it requires high space, it requires high space and cost. It requires high space and cost because of the transformer, because of the midpoint transformer, because of the midpoint transformer. So these are the major drawbacks are there, and meanwhile it requires, the major difference is midpoint configuration, two transistors and one transformer is required. But coming to here, in this full wave midpoint configuration, four transistors are required. However, midpoint configuration cost is very high and bridge type configuration is very low. That is why we have people are referring bridge type configuration, single phase full wave bridge type configuration, R and RL loads. Now in this session we are going to see how single phase full wave midpoint converter will work for RL load as well as RL load. Here the waveforms and circuit diagram exactly quite different when compared to the previous lecture. Now, if you people observe that the circuit diagram for the single phase, single phase, let us take it as a, here we are going to take it as a bridge circuit. Bridge circuit, it is nothing but we have to take it as a, this is, let us take it as a T1, and this is, we will take it as a T2, and this is, we will take it as a, this is, we will take it as a T3, and this is, we will take it as a T4. Here four thyristors I am going to use for the midpoint configuration of the circuit. Now let us take it as a, this is positive supply, we will go it to here, and negative supply we are going to give it here. So here what is the source voltage? Vs. And let us give the names, alternate name, T1 and T2, and here T3, and here T4. T1, T2, T3, T4. Alternatively we are going to switch on the thyristors. Now take it as a one resistive load. Let us take it as a resistive load. This is the resistive load. You people will take it as a resistive load. This is plus minus. This is V0. Now, if you observe that bridge type configuration, how many thyristors are there? Thyristors are SCR, silicon control rectifiers. How many thyristors are there? Here total number of thyristors involved 4, and required number of PWM pulses, 4 driver circuits are required. 4 driver circuits are required. Now we'll see the operation of the circuit step by step, how it is going to vary with respect to the time and how it is going to vary with respect to the duty cycle. We will see step by step now. Let us draw a vertical line. Let us draw a vertical line, and here this is the vertical line. First we will take it as a source voltage. For testing voltage we are going to take it as a one phase, one cycle, and coming to that, this is the second cycle we are going to take, and here duration is omega t, and draw the vertical lines. Those lines will give the clear structure of the operation, and this is the second structure of the operation, and this is the third half cycle of the operation, and this is the third half cycle of the operation, and this is the fourth half cycle of the operation. This is the fourth half cycle of the operation. Now, step by step, we will observe that what is the output voltage we are going to get it. Omega t. Let us take it as a, this is 0, this is also 0, this is pi, this is 2 pi, this is 3 pi, and this is 4 pi. So now coming to here, this is the V naught, and this is, let us take it as a I naught. Let us take it as a omega t, and this will be the I naught, and this will be the Vs, and this will be the V naught. And coming to the next, this will be the let us take it as a VT1 and T2. So any one thing we can take it over here. Now we will see what are the pulses we are going to take it. We will observe here now. Let us take it as a thyristor T1 will be switched on at this position. So this is the one pulse which is going to turn on the thyristor T1. Similarly here thyristor T2 will be switched on. Let us take it as a T2 pulse. Similarly here thyristor T3 will be switched on. Let us take it as a T3. Similarly here thyristor T2 again T3 T4. Alternate thyristors is going to switch on. Let us take it as a pulse here. Now draw the where we are going to give the switching pulses to the thyristors. We will draw here. We will draw these waveforms. And coming to the second direction, how it is going to turn on, we will indicate over here. All straight waveforms we have to draw for clear understanding. And this is also one of the waveform. We can take it here. And finally, we will take one more pulse here. Let us take it as a complete down. And now we will indicate the output voltage. First, we will draw the waveforms, which one is conducting from positive half cycle and which one is conducting for negative half cycle. We will see now. First, positive half cycle, plus minus. Plus means the power will flow like this, and here plus means T1 will be on and T4 will be open circuited. If you observe that, it will go like this way, and it will go towards to the load, and after that it will go to T2 and it will come back. That is T1 under. So for positive half cycle, which one is conducting? T1 and T2. Now the waveform we will see. For positive half cycle, which one is conducting here? T1 and T2. The waveform, it has to be very short. We have to reduce that. And up to this, it is going to conduction time duration, that is alpha 2 pi. And in this time duration, if you observe that, what are the thyristors? Thyristor T1 and T2 are in conducting. So here resistive load, it is nothing but voltage and current both are in phase. Then that is the case. The current shape also will be like this. Then now if you observe that this is also alpha and this is also pi. So here to here again conduction duration will be T1 and T2. Now in this place T1, T2 are not conducting, and from here to here T1, T2 is conducting. Now this is the resistive load condition. There is no energy storage here until and unless we are going to switch on. There is no output voltage and there is no output current. And inductive as well as this is T1, T2, it is not going to conduct anymore. That is why the waveform will be like this. Now again, if you observe that T3, T4 for negative half cycle, if you take for understanding, I'll draw the circuit one more time so that you people can understand clearly how T3, T4R is going to conduct for the negative half cycle. Please observe it here clearly so that you people come to know that how thyristors are working for negative as well as positive half cycles. Now I'll draw the circuit one more time. All of you observe it clearly so that now let us take it as a how I am going to draw the for negative half cycle how thyristors are going to conduct. We'll see here now. Let us take it as a two thyristors here like this, and again two more thyristors will be like this and connected over here, and this is one more positive terminal, This is negative terminal. This is T1. Like this, we will connect the thyristors and we will take the resistive load over here and then connect it at last. Then previously it was indicated that T1, T2, this is T3 and this is T4. Now coming to the point, what we are going to take it here, positive supply is over. Now we are going to take it as a negative supply. Previously it was positive supply, now it is negative supply. Negative supply means this is minus and this is plus. This minus goes to this point. T1 will be reverse bias, it will be open circuited. Then T4 will be conduction state and plus is goes to this terminal. Then T3 will be forward bias, T2 will be reverse bias. Then it will goes the power like this way and it will goes like this and it will goes like this and it will go and it will come back. So this is the current direction for the negative half cycle. For negative half cycle, which are conducting here, T3, T4 are in conduction duration. Now for T3, T4 negative conduction, how output voltage will come? Here it will come like this. And current direction will be, it will come exactly like this. Now this is the complete repetition. Here in this position, there is no conduction duration. That is why I indicated as it is. Now this is T1, T2, this is T3 and T4. From here to here, again it is 0. Now we will take it here and this one will take it as a this one. This is T1, T2, T1, T2. Again from here to here it is 0. From here to here it will be like this. So here voltage follows the current. Here again T1, T2 we will see this. Now here again here to here 0. Again it will take it as a this one waveform will come here and this is also the waveform will be similar. Now previous as I mentioned that this is T3, T4 and this is T1, T2 and this is T3, T4. So like this continuously the thyristors will function alternative waveforms. Here we are using R load, that is the reason we are not getting any negative pulses over in this place as well as in this place. Only we are getting positive directional power supply. Here when compared to the midpoint and here the differences are only we are going to utilize the thyristors and sometimes if required we will utilize little voltage rating of the transformers, but here the overall cost of the bridge type configuration will be less when compared to the midpoint configuration of the circuit. Now coming to here, if you people observe that from here to here T1 it is not conducting, from here to here it will conduct, again there will be a negative pulse. So like this single phase full view bridge type configuration R load circuit waveform will be like this. So these are the operational waveforms of the circuit. Now step by step we will calculate the average output voltage. Similarly previous case if you observe that from here to here conduction duration will be alpha to pi. It means every 180 degree there is a repetition. Then that is the case as I mentioned you previously that what is the average output voltage, how we will calculate here. Here, the average output voltage, it is nothing but V naught average. Complete repetition, it is nothing but at up to 180 degree, it is coming repetition. That is reason 1 by pi integration alpha to pi Vs dt. Then after that, as we know that supply voltage, it is here 100% utilization factor. Then that is the case. Vs is equal to Vm sine omega t and d omega t. Now take it as a here Vm by pi integration sign means minus cos omega t. Let us take it as a alpha to pi. Then again how we will write it here Vm by pi minus cos 180 minus cos alpha. Then finally how can we write it this one? V naught average is equal to minus Vm by pi into minus of 1 plus cos alpha. Then that is the case. Minus minus will get cancelled. Then that is the case. Vm by pi into 1 plus cos alpha. This is the V naught average. Now coming to I naught average, if you derive I naught average, it is nothing but R load. Vm by R into pi into 1 plus cos alpha. So this is the derivation for the V naught average and I naught average. Now coming to the derivation for the P naught average will be multiplication of V naught average into I naught average. So this is the way we are going to calculate the voltage and current and power of the averages. Now let us talk about the RMS voltage. RMS voltage, how we will derive here? V naught RMS is equal to square root of 1 by pi integration alpha to pi Vs square dt. Now if you observe that 1 by pi integration alpha to pi Vs, it is nothing but Vm sin omega t, that is Vm square sin square omega t d omega t. Now let us talk about Vm square by pi square root of integration alpha to pi sin square omega t d omega t. Now V naught RMS is equal to Vm by root pi square root of 1 minus cos 2 omega t by 2 integration alpha to pi d omega t. Then Vm by root 2 times of 2 pi square root of alpha to pi d omega t minus integration alpha to pi cos 2 omega t d omega t. This is the expression for the V naught RMS. Now coming to the second stage, finally how can we write it here? V naught RMS is equal to Vm by root 2 times of pi into square root of pi minus alpha minus sin 2 omega t by 2 integration alpha to pi. Then how we can write it here? Finally, you can write it the formula that V naught RMS is equal to Vm by root 2 pi square root of pi minus alpha minus sin 2 pi minus sin 2 alpha is divided by 2. This is divided by, this is total divided by 2. This is total square root. Then finally Vm by root 2 times of pi square root of pi minus alpha sin 2 pi, it is 0, then that is the case minus into minus plus sin 2 alpha by 2. This is the final derivation for the P naught RMS. Finally, P naught RMS is equal to V naught RMS into I naught RMS. So this is the R load derivation for the full wave bridge type configuration. Previously it was midpoint, now it is bridge type configuration. The circuit will be exactly different and waveforms and derivations will be little similar. So now coming, suppose if we can observe that single phase full wave bridge type configuration RL load, the waveform will be exactly equal, but the circuit will be completely different. Now that circuit diagram we will see now. Now if you observe that this is single phase full wave, single phase full wave bridge model, bridge type AC to DC circuit, bridge type AC to DC converter or circuit with RL load, with RL load. So now take it as a RL load condition. How we are going to discuss? We'll see this one. Now let us take it as a RL load. How we are going to take it as a RL load? Take it as a one voltage source. Little bit you take it over here. Then this is one SCR and another one is another SCR. We will take it over here. This is also another SCR. This is one more SCR. We will take it here. And here one more SCR. We will take it here. And totally we will connect it like this. Then positive is connected to over here. Negative is connected to over here. And here only the difference is R as well as L load. R as well as L load. This is R naught. This is L naught. This is T1. This is T2. This is T3. This is T4. So like that way we are going to represent here. Here in that one the current direction will be I naught. And here R across that is VR naught. Here L across this is VL naught. And total will be V naught. That is V naught. So how we can write it here? V naught is equal to VR naught plus VL naught. So like this way we will write it over here. Now first we will see the waveforms, how the waveforms will come for the RL load condition. The waveform will be little different when compared to the previous one. Now we will take the waveforms for this configuration. Let us take it as a this is source voltage. Up to two cycles we will take here. That is more than enough. This is first cycle and this is second cycle. Only two cycles we will take here for obtaining the full wave midpoint, full wave bridge type configuration circuit. This is the horizontal line and these are the vertical lines we have to draw for each 180-degree duration. This is 0, this is pi, this is 2 pi, this is 3 pi and this is 4 pi. Like that we have to draw, and let us take it as a omega t in terms of seconds. This is the source voltage. Now we will draw the output voltage. Here output voltage, output current are exactly different. That is why I am going to draw here omega t, that is in terms of seconds. Here voltage and current, that is those are enough. Let us take it as a this is I naught and this is V naught. Now we will take it as a pulses. Let us take it as a this is the pulse here for we are going to give for positive half cycle. And similarly here this one will be the negative half cycle pulse. And similarly here positive half cycle pulse. We will take it here. And here we will take it as a negative cycle pulse. For pulses we will draw the waveforms step by step. Just observe it. Here this is the way we will draw the pulses for the waveforms, and this is also another waveform, and this is also another waveform circuit, and this is also another waveform circuit, roughly I'm going to draw here. First positive half cycle, what as I mentioned that first positive half cycle, if you observe that this is plus and this is minus, plus will goes to this point automatically, as I told you that T1 T2 it will going to conduct. Here the difference is inductive load. Inductive load, inductor does not allow sudden changes currents. So it will slowly charge. It will slowly charge from alpha to pi. That case, whatever the voltage it is there, it will appear over here. And after that, inductor, due to this inductor energy, it will continuously discharge. Due to this time, there will be a voltage that is from pi to pi plus alpha. Let us take it as a this is alpha. This is pi plus alpha, and this is alpha, this is pi, this is pi plus alpha. Now similarly for negative half cycle T3 T4 will conduct up to this duration, and it will be indicated as this is the second pulse we will take here up to this position, and this negative pulse will be there here. Similarly this one also charge and discharge. charge, discharge will come like this. And similarly, this is also it will come voltage like this, and it will go like this, and it will come. So this is the way it will continuously operate. This is T1, T2, and this is T3, T4, and this is T1, T2, and this is T3, T4. Here the previous and here the waveforms are voltage waveforms and current waveforms are completely different. And here negative portion of the waveform will exist due to the inductor, because inductor does not allow sudden changes of currents. Slowly it will charge, it will discharge. So this position will be the discharge position of the inductor. So for this condition, how we are going to see, we are going to observe how output voltage waveform, average output voltage, RMS output voltage will vary. For this condition, if you people observe that, so V naught RMS, let us take it as a V naught RMS, or let us first here we will draw the V naught average, there V naught RMS we will draw. V naught average, it is nothing but 1 by pi integral. Previously it was alpha to pi, now it is alpha to pi plus alpha Vm sine omega t d omega t we will take here. Now coming to here, Vm by pi sine omega t, it is nothing but minus cos omega t integral alpha to pi plus alpha. Here negative is, that is why we are going to take it as a pi plus alpha. Now take it as a minus outside, then minus Vm by pi. So integration of cos means apply cos both side, cos of pi plus alpha minus cos alpha, then that is the case minus Vm by pi minus cos alpha and minus cos alpha. So then that is the case 2 cos alpha will come, that is minus minus will get cancelled. Otherwise we will write it in a clear manner, minus Vm by pi minus 2 cos alpha. So 2 will get cancelled, then that is the case V naught average will be, so finally we will draw here V naught average is equal to 2 Vm by pi cos alpha. This is the final formula for the average voltage. Similarly, we will observe that V naught RMS will be square root of 1 by pi integration alpha to pi plus alpha Vm square sine square omega t d omega t. Now this condition, if you observe that Vm by root pi sine square theta means 1 minus cos 2 omega t by 2, apply both the side, integration alpha to pi plus alpha d omega t. This is this one will come under square root, that is why I am indicated here. Now Vm by square root of 2 pi, here pi plus alpha minus alpha will come for the integration. Then that is the case here sine 2 omega will come, sine 2 omega t by 2. This integration will be alpha to pi plus alpha. Then that is the case minus minus will get cancelled. Then Vm by root 2 times of pi square root of pi minus sine 2 pi plus sine 2 alpha, what it will come, sine 2 alpha minus sine 2 alpha. What will happen here? Sine 2 alpha will get cancelled, root pi will get cancelled. Then finally what we will get, V naught RMS is equal to Vm by root 2, that is, so here we can write it here, otherwise I will write it here, V naught RMS is equal to Vm by root 2. So if you people observe that V naught RMS for full wave condition, for full wave controlled bridge type model, V naught RMS is equal to Vm by root 2, but average output voltage 2 Vm by pi cos alpha. So from previous circuit and this circuit, if you observe that at almost same voltage we are going to get it. The thing is here midpoint configuration differences we will see. Midpoint configuration and bridge model configuration. Bridge model configuration. Midpoint configuration we will use two SCRs, and here 4 SCRs we will use, and here high power rating transformer is required. Here it may not be required, may not be required, may not be required. Here efficiency of the circuit is moderate, and here efficiency of the circuit is high. Here efficiency will be very high. And coming to that, cost of the circuit is high. Here cost of the circuit is moderate. Cost of the circuit is moderate. These are the major differences for the midpoint configuration and bridge type configuration. These are the major things we have to observe. 2 SCRs, 4 SCR, transformer required, it may not be required, moderate efficiency, efficiency will be very high, cost is low. These are the major things we have to write down in the examination point of view. Thank you everyone. Thank you so much. We'll see in the next lecture how three-phase AC to DC converters will work and what are their operation. Everything we will draw. Thank you. Thank you so much.